Hello, I am Dr. Matthew Berry from the Mechanical Engineering and Material Science Department at the University of Pittsburgh, and I will be presenting on behalf of Corey E. Clifford. Today we will discuss model form and discretization uncertainty of thermal fluid electric coupled thermoelectric systems. Thermoelectric generators are solid-state devices comprised of hundreds of p-n junctions positioned electrically in series and thermally in parallel. These devices convert a temperature gradient into an electric potential via the Seebeck effect. A single junction within a TEG is shown in Figure 1. When applying TEGs to waste heat recovery, to properly model the behavior, two approaches can be taken. One is an iterative approach to resolve the thermal hydraulic behavior of the waste stream, and using the set information to provide bounds to the TEG to resolve the thermoelectric behavior of the device. This arises from the fact the thermal hydraulic behavior of the fluid is dependent upon the thermoelectric behavior of the TEG, and vice versa. The second is creating a fully coupled multiphysics model, where the behavior of the waste heat stream and TEG are simultaneously resolved, which is proposed herein. The reasoning for the requirement of such high-fidelity models is that in the absence of experimental data for which a numeric model can be validated against, there is much uncertainty. This uncertainty arises in two forms. The first is model form uncertainty, due to the treatment of the turbulence momentum in thermal energy transport equations, i.e. from the use of RANS-based modeling. The second is discretization uncertainty, which is due to the discretization of the governing partial differential equations into a finite volume form. To illustrate these two types of uncertainty, a fully coupled thermal fluid electric model was constructed of a novel thermoelectric device, the integrated thermoelectric device. The ITED is a restructured TEG where the hot side interconnector also acts as a hot side heat exchanger, and is configured to promote the evolution of high convective heat transfer coefficients within the heat exchanger system. This device configuration is shown in Figure 2. And note how it contrasts a typical device shown in Figure 1. The geometry of the device is as follows. The flow channel width was 31.75 mm. The flow channel height was 15.875 mm. The pin fins had the same height as the channel and had a diameter of 3.175 mm. The thermoelectric pellets were the same diameter as the pin fins and had a height of 1 mm. The transverse and longitudinal spacing of the pin fins was taken as 2.5 and 2 times the diameter of the pins respectively. There were 35 p-n junctions within the device, and the load resistance was set equal to the internal resistance as to maximize power output. To properly model this device, a conformal, highly orthogonal hexahedral mesh was first generated using ANSYS ISM CFD, as shown in Figure 3. Care was taken to ensure Y+ on all surfaces for which convective heat transfer was occurring with subunity for the entirety of the study. Using ANSYS Fluent 17.2, the user-defined scalar functionality was employed to model the thermoelectric general energy equation, which represents conduction, Joule heating, Thomson heating, and the Peltier effect. Bridgman heating was ignored. The thermoelectric materials used were silver sodium and NP-type alloys. The electric potential was the sum of the ohmic and Seebeck voltage potentials, where the Seebeck voltage potential was the sum of the Seebeck electromotive force within each pellet. The internal resistance was found via summing the electrical resistance of each element via a volume-weighted average. The current density was expressed via the non-ohmic voltage current relationship. The conservation of current density was also ensured. The boundary conditions of the model were as follows. At the outlet terminal, a zero voltage potential was applied. At the inlet terminal, a current density was applied. All exterior surfaces of the device, except the cold side boundaries, were modeled with a convective and radiative heat transfer coefficient, where the free stream temperature was taken as 300 Kelvin. All solid domain interfaces were modeled with the conservative heat flux and current density. All fluid solid domain interfaces were modeled with the conservative heat flux. Lastly, the cold side interconnectors were exposed to a constant temperature of 300 Kelvin. To model the fluid domain, a Reynolds average and Navier-Stokes formulation of the momentum and thermal energy equations were applied, in addition to the continuity equation. The Reynolds stress tensor, V', V' bar, and turbulent heat flux, V', T' bar, were constrained using RANS-based models. It is noted the system response quantities of interest are the power output of the TEG, the heat input into the TEG, the pumping power required to pass the waste heat through the heat exchanger, the thermal conversion efficiency of the device, and the dimensionless performance index. All thermophysical properties of the solid and fluid domains were taken as temperature dependent. the inlet temperature was fixed at 750 Kelvin, and the Reynolds number was varied between 3 and 15,000. The 5 based RANS turbulence models used were the Spaulding-Ulmarus, K epsilon, K omega shear stress transport, and Reynolds stress models. The first uncertainty quantified was the discretization uncertainty, which arises through the discretization of the governing PDEs into a finite volume formulation. Note that although the finite volume method is energy conserving, it is only first order accurate. To ascertain this uncertainty, 3 successive meshes were used within the numeric model, and the effect of mesh refinement on each system response quantity was determined. Using the grid convergence index, the ASME gold standard for discretization uncertainty quantification, and reporting the uncertainty within a 95% confidence interval, we see that although a grid-independent solution is achieved, there are large amounts of uncertainty associated with prediction of some paramount system response quantities, namely device resistance, generated current, and subsequently calculated power output and device thermal conversion efficiency. To quantify the model form uncertainty, the 5 aforementioned applicable RANS-based turbulence models were employed, and the effect of each model on each system response quantity was ascertained. The uncertainty represents a 95% confidence interval, about the average system response quantity of all 5 turbulence models. It is seen there is large uncertainty associated with the thermal hydraulic behavior, namely pumping power and heat input into the TEG, which subsequently affects the device performance predictions, namely thermal conversion efficiency. The total uncertainty is calculated as square root of the sum of the squares of each uncertainty. If we look at power output and heat input over a range of Reynolds numbers, we see the following. For power output predictions, discretization uncertainty dominates the total uncertainty. It is seen that discretization uncertainty plays a major role in the uncertainty of system response quantities within the solid domains. Conversely, model form uncertainty substantially contributed to the total uncertainty of heat input predictions. Model form uncertainty typically played a major role in the uncertainty of system response quantities within the fluid domain. The uncertainty in system response quantities increases with increasing Reynolds number, and the uncertainty is non-negligible, exceeding 8% for both power output and heat input. The notion that model form uncertainty plays a major role in the uncertainty of system response quantities within the fluid domain is further substantiated by predictions of pumping power, where discretization uncertainty had almost no effect on predictions. The uncertainty with pumping power predictions increased with increasing Reynolds number and reached a maximum value of approximately 12%. Lastly, considering device efficiency, it is seen there's a large, wide uncertainty band, and that both discretization and model form uncertainty contribute to the total uncertainty. The uncertainty at the points of maximum efficiency exceeds 10%. Within this work, the effects of discretization and model form uncertainty on the total uncertainty associated with numeric predictions of system response quantities of a fully coupled thermal fluid electric ITED were demonstrated. Discretization uncertainty namely affects thermoelectric predictions within the solid domains. Model form uncertainty namely affects thermal hydraulic predictions within the fluid domain. The total uncertainty arising from both forms is non-negligible. Due to the interplay between the solid and fluid domains, it is recommended researchers quantify this uncertainty when using numeric models. Due to the large uncertainty arising from the selection of turbulence models, the RANS-based models must be validated to either benchmark quality experimental data or against higher fidelity numeric models before definitive performance predictions can be made. The authors would like to thank the Mascaro Center for Sustainable Innovation at the University of Pittsburgh for providing funding. The authors would also like to thank the Center for Research and Computing at the University of Pittsburgh and the High Performance Research Computing Group at Texas A&M University for providing computational resources.